Howdy, we are greenhouse gas emissions. So here is our video recording link, as well as our team members, the roles, and the minutes they presented. So our motivation. The environmental issue, global temperatures are of course rising. The rise in temperature is linked to greenhouse gas emissions that are largely a product of burning fossil fuels. To combat this, it's important to create effective policy. Climate agreements aim to slow increasing global temperature, and they are necessary to monitor emissions and eliminate high polluters. So on the graph you can see to your right, year is on the x-axis and global temperature is on the y, and you can see a positive correlation between an increase in CO2 concentration and an increase in temperature.
Our mission objectives are to collect data reflecting the location of greenhouse gas emissions around the globe, as well as to collect additional data from a specific location that we think requires further investigation. And you can see the picture below. We have the satellite identifying the location and then the UAV going to the same location to take further measurements. The mission and platform level requirements break down like this. We have mission level requirements saying that the system shall take measurements of greenhouse gases in the lower troposphere. The system shall detect CO2 and CH4, which we've determined are the two most important as well as easily accessible greenhouse gases. The system shall also take measurements globally so that we can identify greenhouse gases anywhere. The system shall have a spatial resolution of less than 100 meters so we can identify greenhouse gases. And the system shall be designed for a minimum mission life of 10 years so that we can both identify greenhouse gases as well as see the time variance of greenhouse gases around the world. For the satellite requirements, the constellation shall have a maximum revisit time of 25 hours. Well, this is a little bit longer than we'd initially anticipated. This is pretty good for a worldwide constellation maximum revisit time. And because we have an aircraft that can exceed those requirements, or like that maximum revisit time, we think that it's allowable. For the aircraft requirements, we have the UAV shall have a range of at least 12,000 nautical miles, and the UAV shall have a loiter time of at least 120 minutes. That'll allow us to go to any location on a continent and then take measurements and return.
So I will begin speaking for the ConOps section of this system. And so our subsystems that are going to comprise our overall system is going to be the satellite constellation, which is going to take the coverage of the entire Earth with just 3 satellites and 120-degree true anomaly phase shift. They're going to be measuring the CO2 and CH4 across all the parts that they scan over using a push broom sensor, which will be talked about later. And UAV deployments will be doing the exact same thing that the satellites are doing. However, they will be doing it at a much more accurate range for CO2 and CH4, and not as good as a temporal resolution as the satellite constellation is, obviously, since satellites can scan the Earth continuously almost twice a day. And the ground stations are going to be the link between the satellites and the UAV systems. There's going to be 2 situated in the North and the South poles, operated by UN appointed technicians. There's going to be an uplink station for the satellites, and there's going to be server rooms of data for the post-processing process, which will be used to actually pinpoint where these greenhouse gases are coming from. And here is a slide showing the concept of operations visually. So I'll just go through the process for each of these systems. You can see in the top right, we got a greenhouse gas satellite, which is one of the 3 that I talked about earlier as part of our constellation that goes downlinks the data to the polar ground station, one of the 2 that we have. And that will go over to the UN, our decision-making body. And they get to decide whether, after that transport phenomena has been determined and we've decided we kind of know where that might be, we decide to put out a UAV system. We send a command to an external communication satellite, which sends the signal to an unmanned aerial vehicle to actually detect with a closer range to see if our transport phenomena is correct. And we actually do see a big enough anomaly to see that someone's violating the climate agreement.
Now we turn our attention to the payload discussion. We are interested in identifying the amount of CO2 and CH4 in the gas, and the best way to do that is through spectroscopy. We pick these three wavelengths, which have been shown to be able to identify CO2 and CH4 through missions like OCO2 and GOSAT. This allows us to fulfill our mission requirements. These wavelengths are all in the near infrared, however, which means that we are going to rely on a substantial amount of reflected sunlight to take data. This is going to define our maximum sensor duty cycle to be around 50% with our orbit. Next, we turn our attention to selecting the actual sensor. We considered three different types in our trade study: a push broom, a whisk broom, and a multi-element whisk broom. The primary criteria for the trade study was a large swath or field of view so that we can see a large amount of the Earth at once and thus fulfill our maximum revisit time requirements. The push broom has a very large field of view that can fulfill our requirements for global coverage. However, it has a lot of pixels, which is going to result in a very high data production rate and power cost. A whisk broom and multi-element whisk broom, on the other hand, has a smaller field of view and smaller swath. However, it has fewer pixels, it has lower data production rates, and lower power and mass cost. In the end, we went with a push broom, even though it has a higher data production rate and power cost, because it can fulfill our requirements for global coverage, which is the primary requirement for the satellite. On the left here, you can see the payload design inputs. That includes the sensor type, the sensor height for both the satellite and UAV, the sensor half angle, the pixel size, the resolution, and the number of sensor bands. Note that this is abnormally low, but because of our very focused goal for the spectrometer, these three bands are sufficient for our purposes. On the right, you can see the design outputs for the satellite payload and UAV payload. We got these using equations rather than finding similar neighbors in actual satellites or similar sensors, because we're going to be designing our own sensors rather than taking a near neighbor off the shelf. We have a data production rate and maximum data generated in some sort of timeline for the mission, as well as relevant mass and power requirements. And these are inputs for the rest of our design process.
The structural configuration of the wing was determined to be cantilever rather than braced because the braced configuration really can't withstand the long wingspan that we have, nor the speeds over 200 knots, but the cantilever would be able to withstand that, and hence that design choice. The mid-wing was decided upon because even though it has poor stability characteristics and requires a higher weight of the loading of the landing gear, it does have really good drag characteristics, which is obviously quite beneficial when it comes to a long-range endurance aircraft such as this. We're able to make up for that loss in stability by adding a 2-degree dihedral angle on the wings and a 50-degree dihedral angle on the horizontal tail, which can help increase the static stability of the aircraft. The chosen airfoil of the aircraft was the LRN 1015. This is based off the RQ-4B Global Hawk, and as their mission requirements are quite similar to ours, we determined that this airfoil would be sufficient for our purposes. And from that respect, the wing thickness ratio is therefore 15%. It was decided upon to have a 5-degree sweep angle because this encourages an efficient form of lift to be generated during flight. And with a long endurance aircraft, we want to minimize the amount of fuel that we're consuming. And so lift being generated by the wings helps to increase that efficiency of the flight. And finally, we chose not to have a wing incidence angle because in ROSCOMs, it recommends to compare against other aircraft with similar characteristics and see what their wing incidence angle are. And in the book, it compares against some long range bombers and transport vehicles, and none of those planes featured an incidence angle on the wings, and therefore we decided to have a 0-degree angle of incidence also. The flap area was determined first by calculating the necessary change in lift at both takeoff and landing. And then from that, we compared against 3 different types of flaps, slotted, plain, and split. And then we're able to calculate the amount of lift that they would be able to generate at those times to match the change of lift to the specific type of flap. It was determined there that flap would be the one to generate enough necessary change in lift. And through the ROSCOMs table, we were able to compare the type of flap to the necessary change in deflection angle, and we decided to have a 30-degree max deflection angle, as anything past that will cause separation in the flow. And then from there, we determined that 40% would be a sufficient amount of area in order to generate enough lift. And finally, there are wet wings, which means there are no external fuel tanks. And so the fuel tank is formed between the torque box of the front and the rear spars. And so the volume was determined by linear interpolation, where T over C is the thickness of the airfoil, C, R, and CT are the chord lengths, and A fuel is a trapezoidal approximation of the fuel area. We then were able to ensure that this would be a sufficient amount of volume by comparing the amount of volume required for our known amount of fuel, which is 14,000 pounds, calculating the volume out of that to be 334 cubic feet. And then we are able to fit 428, which means that we have a sufficient amount of fuel volume.
To select the power plant to be used in the Global Hawk G variant, we first had to get a more accurate estimation of thrust to be required in the mission. To do this, we elected to drop the FAR 25 requirements after receiving SDR feedback, while maintaining our current mission requirements of cruise at 18,000 feet and cruise at 65,000 feet. We also took the wing loading estimated from our maximum takeoff weight and a rough estimate of the area of the actual wings of a Global Hawk. Using this number, we are able to back out on the graph a thrust max required of 4,742 pounds. We verified that against the original power plant used on the Global Hawk B variant, the Allison Rolls-Royce AE 3007H turbofan. This power plant is capable of providing 7,050 pounds of thrust, which gives us an excess thrust of 2,308 pounds. This may seem excessive, but the benefits of reusing an engine far outweigh the benefits of creating a more precisely tailored engine at the expense of great research and development. The planform parameters we selected were very similar to those of the Global Hawk B variant, with a taper ratio of 0.43 as backed out of a 3 view, a sweep angle of 11.7 degrees, again from the 3 view, and a thickness ratio of 15% as defined by the NASA LRN 1015. Although we did not know the actual airfoil used, we elected to reuse the LRN 1015 as this provided the best lift to drag characteristics. We selected to use an incidence angle of 0 degrees because we were not able to determine it from the 3 view, but this is consistent with Roscom's maritime patrol aircraft, which had the closest range to those of our mission, and also helped to reduce drag. We elected to use a dihedral angle of 50 degrees as that would help to reduce drag again and provide better stability in flight, which is very important in imaging missions. Not seen here, we elected to use a V-tail instead of a conventional planform tail because this helps to reduce the induced drag overall of the empennage due to the area rule. To calculate the landing gear disposition, we first selected to calculate the aerodynamic center. While this may first seem unintuitive, the aerodynamic center represents a very conservative estimate of the aftmost CG because this is the minimum criteria for static stability in flight, and as such is a suitable baseline before having all the other masses calculated. We took a very conservative estimate of aerodynamic center located at 35% geometric chord, which we then used the 15-degree rule to calculate the location of the actual gear. We elected to use a conventional configuration consisting of 1 nose gear and 2 main gear. This is the best for our airframe, and from this we elected to do a class 1 gear loading analysis to figure out what percent of the load will be on what gear. For the nose gear, we determined that 7.8% of the load will be there, and that 92% of the load will be on the 2 main gears. These not adding up to 100% can be attributed to truncation error. From this, we are able to calculate our tire parameters of nose gear of 1 tire, 20 by 7.5, and 40 psi. In the main gear, 1 tire on each strut, 36 by 11, and 40 psi.
In order to determine the aircraft CG, we had to decompose the aircraft into its respective groups and attribute a fraction of its takeoff weight to each component. In order to get a first guess at the component weights, we must compare our aircraft with those available in the military patrol plane data in Roscom. We decided that the Lockheed U2 was the most similar plane in terms of size and design, so it was with these weight fractions that we were able to determine the weight of each component. These values weren't adjusted from those provided by the weight fractions except for the weight of the engine group. The engine was initially about half of the empty weight, which was a significant overestimation that pushed the CG unreasonably aft, leading us to re-examine and to adjust to the value seen here. In order to determine the CG location of each component, we estimated the location of a group and then measured directly from the 3 view the component's X and Z location in our designated coordinate system. We assume symmetry about the XZ plane, so there will be no Y component to estimate, which is a fairly reasonable assumption as these values would be fairly small even if we did consider them. When determining the CG location, we consider the loading conditions of an empty configuration with fuel, an empty configuration with the payload, and then finally, the empty configuration with payload and fuel arriving at our takeoff weight. Here's an image showing how we located each component on the plane. We set up our coordinate system on the ground with the x-axis running along the body of the plane and the z-axis pointing up. This was done in such a way that each measured value is to be positive. These values were then entered into AAA, which uses the familiar method of summing the multiples of weight and location and dividing by the total summed weight to determine the CG location along a specified axis. The expected value provided by Roscom for the CG of a military patrol plane is 30% mean geometric chord. As you can see, the values found under these different loading conditions are reasonably close to that value. The only configuration that strays away from that value is the empty weight with the payload, and this is likely due to how far forward and how heavy the payload is. The most aft CG at the 33% mean geometric chord is satisfactory with the most aft allowable CG determined from the landing gear disposition method shown earlier. The most aft allowable CG is approximately 24.95 feet. So although our value is considerably close, we are still comfortable with this result as it is just an approximation. Here are the locations of the aircraft CG under each loading condition. As you can see, there is little travel between each condition, which is favorable for stability purposes. And from all this, we are able to create a CG excursion diagram showing the weight and CG locations under different loading conditions. This provides useful information on how one should go about loading the plane. Considering that loading the fuel first would push the CG aft, nearing the most aft allowable CG from the landing gear estimation, it is recommended that the payload is loaded and attached to the aircraft first.
Now we're going to transition over to our space segment, and especially the functional baseline. So we have designed a 3-satellite constellation, with each satellite being in a 500-kilometer sun-synchronous orbit, each phased about 120 degrees. The sun-circular orbit will be in a noon-midnight configuration, which the longitude at the ascending node, or the LTAN, will be at 1200 UTC. So some of the benefits of this sun-circular noon-midnight orbit is obviously the global coverage. It'll have a short revisit time of about 12.5 hours, which meets our 25-hour requirement. We will have consistent sunlight levels, which is important for our sensors because it'll help us gauge whether or not we have the same greenhouse emissions in India as we do over there in the United States. And then we also have high solar intensity, which is important because our sensors need lots of reflected solar light to get their readings. From this graph down below is a lighting time analysis of our main satellite in the constellation. And you can see that it has high periods of sunlight followed by partial eclipse and a total eclipse. This analysis was taken in the summer, so we're going to have a little bit more sunlight because it is in the summer compared to the winter. The next slide. So in this graph, you can see the 2D view of our revisit time analysis. And you start off with 3 satellites phased 120 degrees apart to maximize or minimize the revisit time. And you can see the 12.5-hour revisit time shown in the pink, which is outputted in SDK in seconds, unfortunately. So 4.5 e to the 4th seconds is 12.5 hours. And then the revisit time gets shorter as you go towards the poles, which is expected with this high inclination orbit. If we go on to this next slide, we have the solar intensity analysis done on our main satellite, and you can see that it jumps between 100% solar intensity and 0%, which is correct for our noon midnight orbit, because when it's in the noon going towards the ascending node, it'll have full sunlight and 100% solar intensity, and as it drops back behind into eclipse on the midnight side, you'll have 0 solar intensity.
The satellite delta V budget is made up of 5 different functions or operations for our satellite propulsion system. As you can see, they're listed on the left and tabulated on the right. I'm going to call out the station keeping operation. It's the largest contributor to the delta V budget and primarily compensates for orbital decay due to atmospheric drag. On the table on the right, you can see that all of these contributions are added together, and a 10% safety factor is applied just to accommodate for any unexpected maneuvers or errors in the model. With this in mind, we selected a chemical thruster system, specifically this off-the-shelf Bradford ECAPS 1 Newton monoprop thruster. It has similar fuel performance to that of hydrazine and a steady state ISP in the range of 204 to 231 seconds. With these equations you will see beneath the picture, the rocket equations, we were able to calculate the propellant mass fraction to be about 19%, which means that if we assume a 500 kilogram satellite, we're going to end up with 97 kilograms of propellant. On the AODCS system, it's primarily driven by this requirement for the payload sensor. In order to get optimum performance from the sensor, we're going to need about 10 millidegrees of pointing accuracy. So in order to determine these accuracies, we're going to use a star tracker that provides its fine accuracy down to the less than 10 millidegrees, which fits our performance requirement. And we're going to use a secondary sensor being a magnetometer just to give us course attitude data and use it as a backup or a redundant sensor to check. For attitude control, we're going to use a set of 3 reaction wheels for 3-DOF control and a 60 millinewton meter second momentum wheel for fine control. We may also incorporate the use of auxiliary thrusters just for momentum dumping for those reaction wheels, and that will use the main propulsion system's fuel. Now, when sizing these reaction wheels, we have to first consider our disturbance environment. We're going to make the assumption that the spacecraft is small and roughly cuboidal, and because of that, we are able to assume that the gravity gradient, solar radiation, and magnetic disturbance contributions are negligible. That leaves only the atmospheric disturbance torque, and that's calculated using this formula you see here. I made the assumption that that difference in CPA minus CM is no greater than 0.1, and that the satellite, the v.n contribution is equal to 1, so a worst case scenario. And with that, I was able to calculate the atmospheric disturbance torque to be 4.13 times 10 to the minus 5th Newton meters. And then at the bottom, you will see this table. These moments of inertia about the principal axes, we're calculating using our basic SolidWorks model. And the H you see is supplied by the reaction wheel system. And using Euler's second law, we are able to calculate the expected angular acceleration rates of the spacecraft, which, as you can see, are enough to compensate for that small atmospheric disturbance torque and give us very fine accuracy with the sensor.
So now for the satellite mass budget, we're targeting a total launch mass of under 1,500 kilograms. So because of our 3 satellite constellation, each satellite's going to have to be under 500 kilograms. With this number, we use SMAD and similarly sized satellites to size each subsystem. And then with this 500 kilograms, we included a 30% margin to give ourselves working room for the satellite's mass to grow over time, which it naturally will. So this puts ourselves at a working wet mass of 380 kilograms. Allocating 27% of this mass for propellant puts 81 kilograms for propellant. And then this brings our working dry mass to 300 kilograms. So some important numbers to look at for our subsystems. The biggest mass contributors are the payload, which is going to be over 90 kilograms. The structure and mechanisms on the satellite, which is going to be over 80 kilograms. And then the power subsystem, which is going to be over 60 kilograms. And that encompasses the batteries, the solar arrays, and all the power distribution electronics. So next, for the satellite's power budget, we size it similarly to the mass budget using SMAD, and then we also use a similarly sized satellite. We use the OCO-2, the Orbiting Carbon Observatory, because it was really similar size and had a very similar scope to what we are doing with ours. So after sizing each subsystem's power requirements, we developed different operational modes that the satellite will be in on orbit. So our first mode is sensing mode. This is where our payload is on, as well as other critical subsystems. And this is on during the daylight hours because our payload can't run during eclipse. Next, we have the communication mode. So this is for uplinking and downlinking, which we do at the poles. So we have our communication subsystem on, as well as the other mission critical subsystems. And then it's important to note that this can happen both in daylight and eclipse because we might have contact times during eclipse. Next is safe mode. This is on normally during eclipse. Save power, and additionally, in any emergency situations where saving power is critical. Then last is the maneuver mode that activates just during orbital maneuvers and turns on and provides power to the propulsion subsystem, as well as any critical subsystems. So next, diving deeper into the power subsystem, there's three responsibilities for the power subsystem. First, we have power generation. The power generation subsystem is going to have to generate power for both the daylight hours and enough power to be stored for the eclipse time. So to accomplish this, we chose triple junction solar arrays, and we determined a necessary area of solar arrays to be 2.64 square meters. This was calculated at our worst angle to the sun of 25 degrees. And we found that this configuration generates 674.6 watts of power during full sunlight. Next, for storing this power for our needs during eclipse time, we have chosen lithium-ion batteries. We determined that these are going to have to be sized at 466.7 watt hours. One of the driving requirements for this is because of our long mission duration. We're expecting around 55,000 cycles of these batteries. So that's a large driving component for that. Lastly, we have the power distribution subsystem. This is responsible for regulating the power that we have generated and distributing it to the subsystems, as well as charging the batteries. So with SMAD, we've estimated this at 30% of our total power subsystem mass at 19 kilograms. Then over here on the right, we see a drawing of the one of our satellite solar panels. You can see the dimensions are 1 meter by 1.35 meters. Together, both the solar panels have a total area of 2.7 square meters, which complies with our requirement needed of 2.64 square meters. Next, for the communication subsystem, our payload is going to be generating 166.65 gigabytes of data every day. And together with our 15.5 downlink opportunities that we have every day, which have a mean access time of 860 seconds, we're having a max data rate of 120.02 seconds. And this is including a 20 megabit per second margin. With these values, as well as our chosen receiver, which is the near Earth network, having a gain of 32 decibels, we have chosen a X-band transmit antenna, which is going to require a gain of 24.19 decibels. This warrants the need for a parabolic antenna because of the high gain, and we've chosen and we have decided on an aperture of 7.9 centimeters. Additionally, to the antenna, we're going to need to have onboard storage in the case of missed downlinks. So we are providing storage for up to 3 orbits of missed downlinks, which is going to mean we need 32.2 gigabytes of storage on board. So for the actual structure of the satellite, we are going to have 2 configurations, a stowed configuration and an on-orbit configuration, so we can launch and fit in the fairing of our launch vehicle. And then we can deploy our solar panels upon reaching orbit to have maximum sunlight. So you can see here on the left, we have the stowed configuration where we have a total volume of 0.7 meters by 1.37 meters by 1.92 meters. And you can see how the satellites fold in parallel to the spacecraft. And then once it's deployed on orbit, we deploy the solar arrays parallel to the spacecraft, having a total span of 3.79 meters, which is greater than what would fit inside of our fairing. Lastly, we have the satellite's thermal subsystem. And so because we are going to be in eclipse and full sunlight, we're expecting temperature fluctuations between -65 degrees Celsius and 125 degrees Celsius. So some of the temperature critical components that we're going to have to worry about are the batteries, which are going to have to be kept between 10 degrees Celsius and 20 degrees Celsius for optimal performance and lifetime, which is going to be really important for our long duration mission. Additionally, electronics in the ADCS subsystem is going to require heating to or temperatures between 0 degrees Celsius and 50 degrees Celsius. So to achieve these thermal constraints, we are going to be keeping temperature critical components inside the satellite where we can control the thermal environment. We're going to be applying thermal control coatings to reject as much heat as we can in full sun to keep the inside of the satellite cool. And then during eclipse, we are going to have insulation as well as actively controlled heaters to keep all the interior components at an optimal temperature. So at the drawing on the right, over here on the right, you can see the different subsystems that we have inside of the spacecraft. We've got the propellant tank, the power distribution subsystem, the ADCS subsystem, which includes reaction wheels, and then the onboard computer. It's important to note that the payload down here is going to require cryocooling, so that's going to be kept separate from the warm components.
So now I'm going to talk about our satellite launch providers that we looked at in a trade study between 3 big Western companies. We decided to just look into the Western since they're the most established companies. We know that China and Russia have their own, but they're not probably going to be as commercially available. And United Launch Alliance, SpaceX, and Arianespace have had a lot of business. Arianespace has had the longest history of having business as a commercial space flight operator. Developed in the 80s, and so we looked at them and also compared ULA and SpaceX together in depth. Vega's rocket, which was developed by Arianespace, is probably the best suited for this mission, but it is unfortunately had only 88% mission success over the 17 launches it's had since 2012, so that was almost immediately booted from consideration, since it's not a very good success rate, especially comparing to ULA's 100% success rate and SpaceX's 98% success rate with their Falcon 9. And so we can see that ULA has been pretty established since 2002, and the SpaceX's Falcon 9 has been established since only 2010, but has had still over 100 launches. So if we look at the next slide, we can see a few other factors that came into determining which is better between SpaceX and ULA for this mission. And overall, we've decided that ULA is the better of the 2 options. We should still look into negotiating with them for pricing reasons, since we can see that the Falcon 9 cost per rocket is $65 million, about 50 million less than the Atlas V, which is around 110 million. However, ULA's performance history leads to better insurance rates for launch. That isn't super readily available information, but probably negotiating with the companies and figuring out more details about that will truly see who's at a better cost. But it seems like from what data information there is out there currently, that ULA will still lead to a lower price in the long run, especially when considering the average launch delay is very good for ULA, as in there's not they have a very low launch delay compared to the industry average of 4.5 months. And so we see here that we have a Atlas V fairing, and we put our satellites into a model of that fairing. So you can see how our chosen topic goes.
All right, so for the ground segment, we decided to use 2 ground stations at Kiruna and McMurdo in the near-Earth network because of our high inclination orbit. The fields of view for each ground station are shown on those plots to the right, and the red line shows a 500-kilometer altitude. We will downlink on the X-band and uplink on the S-band. And as far as the data rate goes, the McMurdo ground station meets our requirements, but unfortunately, the near-Earth network user guide for the Kiruna ground station didn't provide specific information about that. But our spacecraft is designed to store data for a minimum of 3 orbits anyways, so at least we know that all the data will be saved, even if that ground station isn't available. And then here's just a table of the relevant parameters for each ground station, which all come from the user guide. So here's our risk assessment rubric again. Nothing has changed from SDR, so I will just leave it up for a couple of seconds so you can read it. Okay. Here are the top risks. The first 2 are the same as SDR, so I'm only going to cover the new ones. The first new one is orbital insertion failure, which could be caused primarily by the launch vehicle or the propulsion subsystem. And the effects of this could be a damaged spacecraft, bad sensor readings because the satellite isn't in its proper orbit, or possibly an entire mission loss. And to mitigate this, we'll use reliable launch service providers, which I think we've done by choosing ULA. And we'll extensively test thrusters while we're still on the ground. Next is loss of control of the UAV, which could be caused by stability issues or the UAV entering an unplanned flight path, which would obviously lead to an inability to fly on the intended path or a collision with another vehicle or building, and at the very worst, possibly cause a loss of life. To mitigate this, we could implement design changes to improve the stability, which has actually already been done by adding a dihedral to the wings and the horizontal stabilizer to make the aircraft more stable. Or we could look into designing a collision avoidance system. Okay, next up we have the cost assessment. So just a few notes first. All the values were adjusted to fiscal year 20. And the tables on this slide and the next slide are going to show the cost for only 1 spacecraft or UAV, so just a heads up. So our approach for the space segment was to use a combination of CERs from SMAT and component costs if they were available. The ground station cost was calculated using information from the latest version of NASA's MOCS document, and that value was calculated with knowledge that we're going to pass the ground station twice a day for the minimum mission life of 10 years. And the launch vehicle cost was pulled straight from the ULA website. As far as limitations go, these CERs may be outdated, which could make these numbers inaccurate, but we ensured that we stayed within the input range for each of the CERs used. Yeah, so with that being said, our total space segment comes out to around 200 million. So for the aircraft costs, we had to use primarily analogies based on UAVs in a similar size and weight class. So we use a Global Hawk to estimate the unit cost because the design was based on the Global Hawk. And this unit cost includes research and development, procurement, and total program costs according to the source that's listed on that table. And for operations and support costs, we made an analogy to the MQ-9 Reaper because it was one of the few UAVs with ONS cost data available in the same size and weight class as our UAV. So this unit cost includes unit manpower and unit operations, maintenance, support, fuel, engineering and program management, and training. Next, some limitations of this approach are that there aren't many aircraft with similar missions that we can make an analogy to. Another was that the unit cost of this was based on a higher quantity of aircraft available at the time that assessment was written, meaning that this estimate might not be accurate for our mission, which only requires 6 UAVs. So our total air segment comes out to around $252 million for 1 aircraft. Finally, here is the total cost adjusted for 3 spacecraft and 6 UAVs, making the total life cycle cost around $1.9 billion. All right, thanks for listening.